Over the centuries, scientists have solved countless mysteries about the cosmos through careful observation and experimentation. But one of the most enduring mysteries is closest to home. We still have never seen how a solar system like our own is born. Our current model of how planetary systems form is mostly based on extrapolation of data from meteorites and observations of our neighbouring planets. And for the most part, scientists think we've broadly got it right. At least the models we've built seem to make sense. There are, however, stages that have remained somewhat mysterious. Exactly how, when, and where planets form being the big one. But that's about to change. Earlier this year, the James Webb Space Telescope found a baby star hidden in a cocoon of gas. And amongst that gas and dust, planets are being made. For the first time, we've been able to see the very earliest phases of planetary formation. So not only are we finally getting to the bottom of the puzzle, it could even show us something about how our own solar system's planets came to be. Its future planetary system might look like, and dive into how this discovery is reframing our understanding of planet formation across the universe. Given that we live on a planet, have visited 7 others in our solar system, and found more than 6,000 beyond that, you'd think that we should have a pretty good idea as to how planets form. Well, unfortunately, that's not necessarily the case. Much of what we know today is thanks to the analysis of meteorites that have landed on Earth and observations we've made of the planets in our own solar system as they are now. The rest of it has been left up to models and simulations. Why? Well, it turns out the earlier stages of star and planetary formation are extremely difficult to see. It all starts with huge molecular clouds made up of dust and gas particles. As they move around, they create thermal pressure, pushing outward on the cloud. But these particles also have to obey the laws of gravity, just like everything else. So they also pull each other and the cloud inward. This push and pull remains in perfect balance for millions of years, keeping the nebula stable. But a nearby cosmic event, for instance the shock wave resulting from a supernova explosion, can suddenly send everything into disarray. If gravity starts pulling this gas cloud inward faster than the pressure of its moving particles can push back, we get a runaway effect, a gravitational collapse. The dust and gas from the outer regions begin raining inward, and as everything gets denser and hotter, it begins to spin faster and faster, speeding up like a figure skater pulling their arms in. A heat gradient forms, with temperatures reaching more than 1000 Kelvin within 1 astronomical unit of the center, and cooling to 400 Kelvin at a distance of 5 astronomical units. Over the next 100,000 years, most of the mass concentrates in the middle of the cloud, eventually forming a protostar. The rest is dispersed outward, forming a protoplanetary disk of swirling dust, a womb for this stellar embryo. It's all this gas and dust that make the stellar formation process so tricky to see. Our telescopes can't peer through it, but as technology has improved over the decades, we have started to catch glimpses. In 2013, a team led by Emilia Stutz turned the attention of the Herschel Space Telescope to the Orion Molecular Cloud Complex, the biggest site of star formation near our solar system. Known as the Herschel Orion Protostar Survey, or HOPS, it searched the Messier 78 nebula. HOPS found 15 new protostars, each with masses between 1/5 and 2 times that of the Sun. These protostars had never been seen before because their gas envelopes are so cold, heated to just 20 degrees above absolute zero, with the protostars hidden deep inside. This indicates that the star hadn't yet had time to warm the gas. They are young. In fact, Stutz and her team believe they are some of the youngest protostars to ever have been found, finally giving us something to compare our models to. But the initial star formation isn't the only process we know very little about. How planets themselves come to be is just as much of a mystery. Our simulations tell us that in the main body of this disk, the dust and gas particles begin to accrete. They condense into microscopic solids, which clump together into larger and larger grains over millions of years. Eventually, these solidifying clumps of spinning debris become planetesimals, the building blocks of primordial planets spanning several kilometers across. If enough come together, either via gravity or collisions, they can form a planet. The problem is, we've never seen most of this happen. We've found young planets. This one is 4 times the mass of Jupiter and less than 5 million years old. And this gas giant is even younger. Its star is only 2 million years old. But that's as early as it gets, and they are already fully formed objects. There's hundreds of thousands, if not millions of years gap to fill in. That is, until now. 1,300 light years away, in that Orion Nebula, a baby solar system is being born, and we're watching it with our own eyes. Well, James Webb's lens. This is HOPS 315, a star that's less than 150,000 years old and 0.6 solar masses. It's still growing, feeding on an envelope of dust and gas that hides in a cloudy veil. But incredibly, researchers found a gap in the clouds and managed to snap a photo. And they saw something extraordinary. Webb's infrared spectra showed the presence of both warm silicon monoxide gas and tiny silicate crystals near the young star. We were witnessing the moment gas condenses into a solid for the first time. This is a big deal because as a protoplanetary disk starts to cool, compounds begin crystallizing in a specific order based on their condensation temperatures. This is known as a condensation sequence. We can infer this sequence from our understanding of chemistry and our analyses of primordial asteroids, which are like time capsules of our early solar system. The oldest condensates trapped in these asteroids are calcium-aluminium inclusions, or CAIs, and crystalline silicate materials. The fact that we saw both silicon monoxide gas and solid crystalline silicates around HOPS 315 indicates that this star and its system are at the very beginning of their formation. In other words, we were watching the very first stage of planet formation as it's happening for the very first time. This was a major breakthrough, and as lead author of the landmark paper, Melissa McClure puts it, for the first time, we've identified the earliest moment when planet formation is initiated around a star other than our Sun. They wanted to explore further, so Professors Melissa McClure and Merrill Van 't Hoff focused the Atacama Large Millimeter Submillimeter Array Telescope, or ALMA, on this baby star. Whilst James Webb Space Telescope revealed the warm inner regions of a young star through infrared light, ALMA specializes in observing much colder material, the dust and gas that emit millimeter and sub-millimeter wavelengths of electromagnetic radiation. This allows astronomers to trace the chemical composition and structure of molecular clouds. By combining the two observatories, McClure and Van 't Hoff could connect the dots. James Webb found the evidence of early planetary formation, and ALMA pinpointed where in the disk that process was taking place. What's most interesting about this is that it's roughly in the same region around HOPS 315 as asteroids made of similar materials are found around our Sun. We don't know exactly what this means yet, but it suggests that the same early building steps for planets may happen in many young systems. And there's more. It's worth mentioning that although silicates were found, the outflow jet they studied is actually suspiciously low in silicon, the most important element for making silicates and therefore planets. There's just 2% of what McClure expected relative to the amount of carbon they found. But this isn't a bad thing for planet formation. McClure says that may be a hint that planetesimals are already forming there in a similar way that they must have in our solar system. An intriguing finding given the system is so young. We are finally able to timestamp the beginnings of planetary formation to less than 150,000 years after a star begins to form, which is turning our models on their heads. Initially we thought gases only began condensing once the central star formed a Class II system, or when the stellar envelope is mostly gone, the star has stopped growing, and what remains is a relatively calm, well-behaved debris disk. But over the last decade, mounting evidence from several young protostars, like these, have suggested that planet formation actually starts way earlier. Still, these disks were not well categorized. HOPS 315 has gone one better and confirmed our suspicion. But there's still one mystery about the nebula hypothesis. Scientists have long struggled to explain how millimeter-sized chondrules grow into rocks kilometers in diameter. Small particles don't naturally stick together, and medium-sized objects fall into the star within about 100 years due to gas drag. One proposal is that dust collapses in pockets of gravitational instability, directly forming planetesimals, a rock emerging from a sandstorm. By repeatedly observing how the gas-to-solid ratio changes in HOPS 315, scientists can uncover how fast solids grow within the inner disk, what might limit their coalescence, and how that affects planet development. But perhaps most impactful of all, the HOPS 315 system is one of the best that we know to actually probe some of the processes that happen in our solar system. By comparing HOPS 315's dust chemistry with meteorites from Earth, scientists can see whether the same condensation sequences and elemental distributions that shaped our planets occur in other parts of the universe. We can finally test our models against the real thing. But just as with anything in science, as soon as you make a discovery, it leads to many questions. So, what's next for HOPS 315? How many planets will it have? Will they be split into small, rocky planets in the inner solar system and icy gas giants in the outer reaches of the star's influence? Well, the condensation sequence in the protoplanetary disk has a direct impact on what kinds of planets form and where. This lets us at least make an educated guess. Since the early disk isn't uniform in temperature, different compounds will condense first in different parts. One feature of this is called the snow line, the point beyond which conditions allow ices to form. In our early solar system, this line was at about 2.7 astronomical units for water ice. Beyond this snow line, ice and dust accumulate, slowly snowballing into giant planetary cores. The colder temperatures out here also mean gas travels slower enough to be captured by the growing gravity of these frozen cores. Eventually, enough gas is captured to form a planet, and a gas giant is born. This process happens very fast. We think it's how Jupiter and Saturn formed in as little as 10 million years. Meanwhile, on the other side of the snow line, ice and volatiles are completely vaporized. Here, only materials with very high melting points like iron, nickel, aluminium, and rocky silicate survive. By now, most of the gas in the system has been captured, either by the growing star or the gas giants, meaning there's almost none left for these longer gestating worlds. The result is smaller, rocky planets like the ones we see in our inner solar system, including Earth. We don't know how many planets will form around HOPS 315, but we'd expect to see a similar setup to our own solar system, with inner rocky worlds and outer gas giants, although we still can't rule out planetary migration and hot Jupiters. Given that the current beginnings of planet formation are happening at the approximate location of our asteroid belt, one question is whether HOPS 315 will have one. Ours sits between 2.2 to 3.2 astronomical units from the Sun, and we've already established that asteroid belts aren't a feature unique to us. In 2001, researchers found the first asteroid belt outside of our solar system, 70 light years away around Zeta Leporis, a star 1,000 times older than HOPS 315. But whether one develops around this baby star depends on a few factors. We have our asteroid belt thanks to Jupiter. Initially, the region between Mars and Jupiter was full of dust and planetesimals. There was plenty of material to form another planet. But once Jupiter formed, it got massive fast, and that strong gravitational pull and orbital resonances disrupted the surrounding region, halting accretion and trapping planetesimals in stable orbits around the Sun. This left behind a population of primordial space rubble that never coalesced into a planet, instead becoming the asteroid belt we know today. So one way for HOPS 315 to end up with an asteroid belt is for it to create a planet with enough mass to cause a gravitational disturbance like Jupiter did. But if a large enough planet never forms, HOPS 315 could end up with an intermediate world around the snow line, something our own solar system never developed. So, HOPS 315 is a portal to our past. Studying it is like looking at our own solar system 4.6 billion years ago, when Earth was still a dispersion of gas and dust. But its discovery also raises big questions. How common are solar systems like ours? Does planet formation always start at 2.2 astronomical units? How fast does the disk go from microscopic dust to planetesimals? To answer these questions, researchers are eager to start expanding the search to more very young stars to see if they can spot any others like HOPS 315. If multiple systems show the same hallmarks of creation, we'll have found a protoplanetary goldmine, a wealth of observations and data to pore over to better understand our origins. Whatever they find, one thing is for sure. We were once a swirling cloud of dust, and billions of years from now, we'll be dust again. So perhaps, while we're here, we should make the most of it. I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter